All right, chapter 11 talks about the fundamental theorem of finite abelian groups. And this chapter is pretty exciting because it gives us a lot of information about classifying finite abelian groups. So let's get started. We're going to start with a pretty big theorem, Theorem 11.1. It's the fundamental theorem for finite abelian groups, and it says every finite abelian group is a direct product of cyclic groups of prime power. Moreover, the number of terms in the product and the orders of the cyclic groups are uniquely determined by the group. And just to be clear, these are external direct products. So since every cyclic group of order n is isomorphic to Zn, every finite abelian group G is isomorphic to a group of the form Zp1 raised to the n1, external direct product Zp2 raised to the n2, continuing your external direct products all the way down to Zpk raised to the nk. These PIs are not necessarily distinct primes, and the prime powers are uniquely determined by G. When we write a group in this form, we are actually determining its isomorphism class. So this is what we would call determining the isomorphism class of G. So when we want to think about the order of G, our order of G, if it's prime P, then the partitions of K would be 1. So the possible direct products for G is just Zp. Now, if our order was P squared, then we could have 2 or 1 plus 1. So that means it could be isomorphic to Zp squared, or it could be isomorphic to Zp, external direct product Zp. And it continues on, and we are given in our book up through the order of P to the 4th. This table might be handy to look at when you are trying to determine the isomorphism class of an abelian group. We do have a greedy algorithm for an abelian group of order P to the n. The first thing that we want to do when following this greedy algorithm is compute the orders of the elements of the group G. Then we will select an element, call it AI, of maximum order, and define G1 to be equal to the cyclic subgroup generated by AI, A1. We set I equal to 1 here. If G is equal to if the order of G is equal to the order of GI, we can stop here. Otherwise, we replace I by I plus 1. We select an element AI of maximum order P to the K, such that P to the K is less than or equal to the order of G divided by the order of GI minus 1. And none of AI to the P, AI to the P squared, etc. is in GI minus 1. We define GI to be equal to GI minus 1 internal direct product, the cyclic subgroup generated by AI. At this point, we would return to step 3, check and see if the order of G is equal to the order of GI. If it is, stop. Otherwise, we continue this process going 3 through 5 repeatedly. Now this makes more sense with an example. So after we get a corollary here, we will do an example. Looking at our corollary, talking about the existence of subgroups of abelian groups. If M divides the order of a finite abelian group G, then G has a subgroup of order M. This tells us a little bit more, yawning over here. This tells us just a little bit more about the subgroups of abelian groups, which we haven't had a ton of information on previously. Let's look at example 1 now. We are saying let G be equal to this group under multiplication mod 135, and it says determine the isomorphism class of the group. Alrighty, so I'm going to jump down here to the solution. I'm going to talk you through it. So first, we have our group G under multiplication mod 135. The order of G is 24. So since it's order 24, we know that it's isomorphic to one of the following. It's either isomorphic to Z24, which happens to be isomorphic to ZA external direct product Z3, or it's isomorphic to Z12 external direct product Z2, which is isomorphic to Z4 external direct product Z2 external direct product Z3, or it could be isomorphic to Z6 external direct product Z2 external direct product Z2, which is isomorphic to Z2 external direct product Z2 external direct product Z2 external direct product Z3. I don't think I said too many Z2s. But so really we have 3 different options that we're looking at, right? We have that it could be this, this, or this. We have 3 different options of what it could be isomorphic to. To determine which one, we need to determine the orders of elements in the groups. So, for example, the order of the element 8 is 12. So this third option down here is clearly not the case. So at this point, we could cross that guy out and say that is not it. And that's because there's nothing in that that could have order 12. Alrighty, so then we could consider the element 109 and its order, or we could even look at the element 134 and its order. Both of them have order 2. Since both of them have order 2, this actually implies that G is not isomorphic to Z24. Look back at your theorem 4.4 for understanding why that is. So since there's 2 elements that are of order 2, it cannot be a cyclic group. Therefore, we get that G is isomorphic to Z12 external direct product Z2. So we could say that G is equal to the cyclic subgroup generated by 8 internal direct product, the cyclic subgroup generated by 134. Now we have a few lemmas that we are going to end with here as we're working through our chapter with our examples and theorems and definitions and lemmas and corollaries, and then we'll see a lot more examples when we work through the chapter 11 examples. But our first lemma here says let G be a finite abelian group of order P to the nm, where P is a prime that does not divide M. Then G is equal to H internal direct product K, where H is defined as X, an element of G, such that X to the Pn is equal to E. And we have K, which is defined as X elements of G, such that X to the M is equal to E. And it tells us then that the order of H then has to be P to the N. Our second lemma says let G be an abelian group of prime power order, and let A be an element of maximal order in G. Then G can be written in this form: cyclic subgroup generated by A, internal direct product K. And two more lemmas to finish us off. A finite abelian group of prime power order is an internal direct product of cyclic subgroups. And lemma 4, suppose that G is a finite abelian group of prime power order. If G is equal to these internal direct products of H's, and G is also equal to these internal direct product of K's, where H's and K's are non-trivial cyclic subgroups, with these inequalities holding true, then M has to equal N, and HI equals, the order of HI equals the order of KI for all I. So that is chapter 11. Again, if you have any questions, feel free to email me, let me know. And I will be posting a video as well of example problems from the book, from the exercises in chapter 11.